Welcome to part 2 of our webinar, First Article Approval Success, focused on cold start new awardees who have contracts to produce low quantities of replacement part castings for legacy weapon systems. In part 1, we presented these insights about launching new suppliers of metal casting designs. First, once a casting design has been established, producing it successfully in a first attempt, including approval of a first article inspection, involves intentional collaborative manufacturing engineering of the chosen mold cavity making process and the tooling design and construction. All the way from the mold cavity is formed and assembled through fixtures to check as cast dimensions along the casting finishing processes, and to and through the machining process choice and its fixtures. In part 1, we focused on the elements and complexities of establishing the as-cast shape and its solidification integrity according to specifications. In part 2, our focus will move downstream into the machining and perhaps fabricating some of the as-cast features into a final net shape. Second, in the case of a new supplier launching an existing casting design, it is rarely recognized that all of the prior manufacturing engineering that resulted in an approved production is now lost. The tooling may exist, but the manufacturing engineering of that tooling into the prior metal casting supplier's team's processes is lost. The new supplier may choose to produce the casting in a different mold cavity making process, so existing tooling may not even be applicable. Third, in a worst case, and in the target area of this webinar's 2 parts, is the cold start new awardee for a DLA legacy casting for an aging airframe replacement part. Typically, tooling is lost, no solid model of the design exists, and only a 2D drawing and a legacy technical data package exist to start a fresh manufacturing engineering pathway to approved producibility. Further, 70% of these cold start new awardees have become machine shops who may not fully realize the complex manufacturing engineering of as-cast surfaces that lies before them. In all 3 situations, a machine shop and/or a fabricator will be the capstone player in an up to 5 partnering businesses that convert a mostly as-cast shape into a final net shape. This part 2 is intended to help the machine shops and/or fabricator partners in this collaboration, and who may be the contract holder, be successful in first attempt, first article inspection approval. As in part 1, I will open up a questions box to accumulate your questions and comments real time as we continue. At the conclusion of our presentation, I will return to lead the discussion with you. Leading us off will be our American Metal Casting Consortium casted partner, Dick Tiano. Dick is a manufacturing technology expert, and he will explain the machining castings in which the fixtured surfaces are all as cast, and the final net shaping of as-cast surfaces is surprisingly few. Here is Dick Tiano.
Hi, I'm Dick Tiano. We have learned that machine shops as small businesses, separate from metal casting businesses, play a dramatically increased role in bidding for DLA cold start legacy castings. More broadly, machine shops, sometimes as fabricators as well as separate businesses, are the most common way that a metal caster as cast surfaces are brought to final net shape. A question that is rarely asked: is the machining of castings to final net shape different than machining a net shape from a wrought metal block, a bar, or other primary wrought shape? The answer is yes, significantly different. In the big picture, in a soundbite, the difference is this: machine shops who are good at net shaping castings focus on the fixture design that enables consistent setup against as-cast surfaces. Machine shops in general realize that wrought shapes are consistent in exterior profile, and the focus is on the type of machine tool, its basic orientation, its cutting pathways, and the number of axes needed to accomplish net shape. Fixture design is focused on orientation and axes, not consistent setup on surfaces that may vary. Net shaping of castings involves a very low percentage of overall surface area. Even casting that is extensively machined to reach net shape would still be 70% as cast. Typically, the machining to upgrade a casting to net shape involves 10% or less of the total surface area. Machine shops who are good at machining castings are also good at collaborative manufacturing engineering, as the as-cast surfaces that will be touched by the first, perhaps only, machining fixture. Consistent tolerances on those surfaces is critical, and the key to consistent tolerances is to limit the degrees of freedom in the way those surfaces are formed in the casting's mold cavity. Finally, when two or more setups, meaning two or more fixtures, are needed to net shape a casting, it is a good practice to set up on the machine surfaces from the first machining operation. When more than one fixture is involved and production volume warrants it, it's a good practice to set up on a machining cell for each machining setup. As a result, castings don't remain in intermediate inventory waiting for the availability of the next machine tool. Often, such a cell involves older technology, less than automated machine tools that otherwise sit idle. The best way to illustrate the differences in machining castings is to look at examples. First, for the sake of comparison, we will look at an aluminum open die forging machined to net shape with 98% of the original wrought shape converted to chips. It is a critical service component for a military helicopter. We will compare that aluminum component with a critical service steel casting that holds on to the rear axles of a Class 8 truck with only 1% chips. 99% of the surface area is as cast. Then we will look at examples of castings with their machine tools, fixtures, and setups to result in a 60%, 35%, and 5% chips. Here are those two critical service components I mentioned. The aluminum structural member for the military helicopter is machined from an open die forging that begins at 2,000 pounds and finishes its net shape at 49 pounds, 98% chips. The steel casting, 4 of them, hold 2 rear axles of an over-the-road 18-wheeler to its frame. Through innovative manufacturing engineering of the mold cavity making process, the only feature machined on the casting is a bored hole for the shock absorber mounting pin encircled in black. 2 totally different kinds of machine shops made these 2 final net shapes. Next are 3 examples of design and machine tool choice for castings machined to net shape by a shop that specializes in castings. First, a very simple sand cast ductile iron casting machined on an old school horizontal mill. It uses 2 simple universal clamping fixtures, and even with all of the mill's surfaces on both sides and drilled and countersunk holes, the remaining as cast surface is still about 40%. Next is a sand casting aluminum casting with specially designed fixtures with only 2 setups to machine the castings set up on the 3 fixtures. Like the ductile iron casting, it was coated before machining. Despite more complex machining orientations, the remaining as cast surfaces are much greater, about 65%. In the second fixture, 2 castings at different stages of completion are set up to use the same machine tool for machining different features. Next is an uncoated steel investment casting that takes advantage of the dimensional accuracy for the investment process to eliminate facing off of the mounting surfaces for the 3 drilled and tapped holes. It also takes advantage of the as-cast cavity at the center of the T-bar feature that eliminates machining of the cavity and a separate setup. The remaining as-cast surfaces from the accuracy of the investment process is all the way up to 95%. Drilling and tapping the holes in the dogleg feature is cleverly accomplished with a simple fixture mounted on the chuck of a lathe. The drill and tapped holes in the ends of the T-bar are accomplished in a simple clamping fixture that captures the ends of the dogleg to securely complement the clamps against the machining forces. Now, I will turn our discussion to Mike, who will explain in more detail the collaborative manufacturing engineering among the mold cavity tooling builder, who builds the solid models enabling machining, fixture and design construction, the metal casters manufacturing engineer, and the machine shop's manufacturing engineer for machine tool choice and fixture design.
We've now seen the very high percentage of as-cast surfaces in casting's final net shape. So how can a machine shop whose usual business proposition is to convert simple shapes into complex net shapes by making chips, make a lot fewer chips and be successful? Another perspective is, how can as-cast surfaces with variations that we have classified in our part 1 of our webinar that are largely net shape already be targeted and clamped efficiently to enable much fewer chips to be removed to reach final net shape? Is there a business case and margin to be captured in being capable in the machining of castings? Well, there is a yes to both questions. And how the yes is achieved is the nugget of wisdom. The surface profiles of castings, depending on the mold cavity making process and the mold cavity tooling design, can vary considerably. Not only vary in dimensional capability from one dimension to another, but also vary in surface smoothness depending on what was connected to a surface in the process of filling the mold cavity and enabling solidification integrity to meet specified mechanical properties. So, the first challenge in machining castings is to minimize those variations on the as-cast surfaces that the machining fixture or fixtures will touch. The objective of controlling those fixture target surfaces is to minimize the variation in position and size of the as-cast features that the machine tool's cutting edge will engage. In other words, enough machine stock thickness in the correct location to mill or turn a surface to net profile, or sufficient as-cast position accuracy to drill or bore a hole with correct net size and position. The only way to make all that happen correctly for first-time, first-article inspection approval is to engineer all of the tooling from the mold cavity to the machining fixture intentionally from the outset, and use the principles of geometric dimensioning and tolerancing to enable that intentional manufacturing engineering. Foremost in making that intentional manufacturing engineering of all the tooling is the mold cavity tooling builder. Although guided by the metal casters and machine shops' processes and preferences, it is the mold cavity tooling builder who enables the milled, drilled, bored, and turned surfaces to be upgraded in the correct positions with respect to all other as-cast surfaces. In the most challenging instance, the cold start new awardee of a contract for a legacy airframe casting is a machine shop who would have no idea who the capable mold cavity tooling builder might be. And at the point of award, the cold start new awardee may not yet have identified who the metal caster will be. It is the metal caster who has the ongoing relationships with mold cavity tooling builders in their geographical region. So, the first step for the machine shop awardee is to investigate metal casting business partners who have the mold cavity making processes specified on the old 2D drawing or have the processes that would be logical based on the drawing's requirements. Upon choosing a metal casting business partner, the single most important next step toward first article, first inspection success is to jointly choose the best mold cavity tooling builder who the metal caster routinely uses and who has the capability and willingness to collaborate over the engineering of the entire tooling system, from the empty mold ready to fill and the final as cast and upgraded surfaces that will meet all dimensional tolerances and surface finish specifications. As we learned in part 1 and are continuing in part 2, that's not a slam dunk. Before we look at examples of how all this works, here are the key elements of what the mold cavity tooling builder can contribute to success. Build 3 solid models from the 2D drawing, replicating the dimensions, tolerances, and surface specifications. In other words, a solid model from the 2D drawing as is, no changes. Then, modify that solid model to describe how the mold cavity will actually be made, where an as-cast surface will be upgraded by machining to achieve the tolerance and or surface finish requirement. Add machine stock to those surfaces. Where a feature might be added to the casting by weld fabrication, make provisions on the as-cast surface for that addition, such as a bored hole for a weld-in stud or a weld chamfer for a weld-on plate. Mold cavity element construction, including additive manufacturing, mold cavity attachments for filling and solidification integrity, and mold cavity size increase for pattern maker's contraction rate. Now, let's look at real machine casting examples of how all this can work for the benefit of a cold start new awardee machine shop.
To review the 3 solid models built by the mold cavity tooling builder, here is the process in the context of launching a cold start Defense Logistics Agency replacement part. This one is a maintenance access door for one of the Navy's shipboard machine guns. The second solid model. Add the pattern maker's contraction rate to all features, making them bigger by the factor of the rate chosen for the alloy involved. So that means that all of these features of the first solid model of the finished part are now larger than that by the amount of the rate of pattern maker's contraction. Not all features will have the same rate depending on mold constraint factors that may restrict the contraction of the metal as it cools. And all metal casting alloys have different pattern maker's contraction rates. This is an aluminum silicon alloy A356. Also added to the second solid model are the parting planes. There's a parting plane across here. Draft is on this surface. All of the matched lines for the top and bottom part of the mold, which will be across here in this parting plane, as well as matched lines for core assemblies. Where draft is not allowed, additive manufacturing technology may be deployed to make mold components to eliminate draft where it's not allowed. Machine stock has been added to as-cast surfaces that will be later machined to final net shape profile. And here we see the surface that has machine stock added for milling flat later with respect to datum A, which is the bottom surface. And then a groove will be machined across the rectangular profile for a seal ring. And then finally, all of the process interface geometry to fill the mold cavity, to vent gases from the mold cavity as the metal flows in, and reservoirs of liquid metal strategically located to feed solidification shrinkage to set up the mass and temperature gradients to achieve the solidification integrity required for the specified mechanical properties. The third solid model. As a reminder, typically all three solid models are built by the mold cavity tooling builder. For that reason alone, it is important that the machine shop and metal caster choose a mold cavity tooling builder with the technical capabilities that enable collaboration in the development of that second model. Now, as a consequence of that collaboration, the third solid model becomes the basis, the key tool in the path to a first-time, first article inspection approval. This third solid model has these attributes that enable fixtures and gauges to be built for accomplishing dimensional and surface finish compliance with the legacy technical data package specifications. Here are its attributes. First, enlargement for pattern maker's contraction has been removed. Second, process interface geometry has been removed, but the stubs of contact surfaces remain. They are slightly raised to indicate their locations and flat. In reality, they will be lightly ground to match the surrounding as-cast surface as closely as possible, and then media blasted to match the surface finish as closely as possible. But they will be wavy and unreliable to be touched by fixture targets. Third, draft remains, as do the match lines of mold parting, core partings, chill profiles, and vent contacts. And fourth, machine stock remains on as-cast surfaces to be later machined to final net shape. So, the third solid model is the basis of fixture and gauge design to avoid touching inconsistent surfaces and allow consistent setups on as-cast surfaces that will always enable accurate upgrading of other as-cast surfaces to final net shape.
In all phases of casting design and manufacturing engineering, the principles and capabilities of geometric dimensioning and tolerancing are the most powerful tools for casting dimensional consistency and compliance with tolerances. Because castings are the most 3D of any metal component form, the 3D nature of as-cast surfaces includes draft, mold parting lines, and mold element assembly match lines, and even more significantly, the tolerance types within the GD&T system enable dimensional compliance of hand cut and ground surfaces where prior connections to fill the mold, feed solidification shrinkage, and vent gases were attached. Two among the 14 specific categories are especially powerful in casting design. Those are position of a feature and profile of a surface. These are so powerful because they control not only size, but they also control two of the other four fundamental categories of tolerance. Specifically, position is a location capability, but it also controls size and orientation. Profile is a location capability, but it controls size, form, and orientation. Due to their powerful nature, utilizing position of a feature and profile of a surface can make castings more likely to be approved dimensionally at first article inspection. But our subject doesn't involve design. Are GD&T principles and capabilities relevant to meeting the dimensional tolerance requirements of a legacy casting with a cold start from a 2D drawing? Yes, they certainly are, and here's how.
So here we see the solid model, third generation solid model, poised above a generic fixture that represents gauges for processing and holding the casting for processing during finishing operations, straighten the casting after heat treatment, and ultimately these principles shown in this little generic fixture represent the machining fixture. So we call this a functional gauge if it's used for the finishing processes, because not only does it gauge the casting by its primary datum compliance with respect to the 2D drawings requirements, but it also holds the casting in a way that enables a processing step like grinding to occur at the same time. So here's how these functional gauges and fixtures work. The blue pins are the datum A targets for checking the flatness of the casting with respect to its overall finished assembly and machining surfaces. If the casting is not flat or twisted in some way and not sitting reliably flat on these three primary datum targets, then the casting will not be machined uniformly across its entire profile. There'll be thick and thin areas in the walls across the entire rectangular profile, which would ultimately result in rejection. There are also pins here on this, which is datum B, 2 pins, which is the secondary datum targets, and they touch the casting, and notice that they are smaller. They touch the casting on the drafted surface. So if the casting sits flat on the datum A targets, then the draft on this surface doesn't matter because these smaller pins will touch the casting at the same elevation. As long as the pins touch the casting on a drafted surface at the same elevation, we learned in part 1 that draft is really an offset and a draw length. And if you touch that draw length at the same elevation across the drafted surfaces, then the casting will sit reliably against those pins and it's an accurate location. Draft doesn't really interfere with accurate location if the pins touch at that same elevation based on the offset versus draw length of a draw angle. This single pin is over here on datum C, and so if you push this casting against the datum P pins and push it against the datum C pin and pull it down onto the datum A targets here, and it sits reliably flat as you do that without gaps on datum B and without gaps on a gap on datum C, then it is a casting that is going to assemble correctly. If it's unmachined, if it's machined, it'll sit into the machining fixture correctly, and it's okay then to proceed with the grinding operation or whatever the functional gauge is intended for to hold the casting for finishing processing. So in other words, every casting, 100%, goes into these gauges and is checked first for reliability of its flatness and straightness, and making sure that if you proceed with the next step, which in this case would be grinding the parting plane here on the surface where the mold parting is defined, and there's a match line there between the top and bottom half of the mold, well then it's you can be assured that proceeding with that next finishing step will result in a casting that will either assemble correctly and or fit correctly in the machining fixture. So these are the principles that are involved in these fixtures that are used for processing as cast surfaces. Well, here's a common mistake. What we see here is solid model number 3 and that generic fixture. This is the datum C target that we talked about before, and this is the remains of the process interface geometry that was cut off. It's a stub that is ground flat by eye-hand coordination by an operator, and that stub then is ground as closely as possible to the adjacent as-cast surfaces. But it's going to be wavy, and it's going to have some high spots and low spots, might even be slightly below the as-cast profile that's neighboring that grinding operation. It's media blasted to make the ground surface look as close as possible to the as-cast profile that is neighboring this area where it is ground. But here's the issue. If the target touches one of these stubs that has been ground and processed, then we are likely to violate this 30 thousandths total wide zone for the position of the drilled holes on the machined face opposite of datum A. So all of the tolerance that we are shooting for hole position can be violated simply by targeting against a surface that has been cut off and ground like this.
To conclude our discussion regarding geometric dimensioning and tolerancing principles and capabilities as applied to functional gauges developed from the third solid model, here's an example that illustrates 3 of the truths about preparing castings for successful first article approval. First, the casting surfaces are 95% as cast. Second, it illustrates go, no-go gauging of individual features without respect to the fundamental component assembly datums, as a preface to functional gauging of those same features with respect to those fundamental assembly datums. Third, it illustrates how a machining fixture can have a dual function, most significantly as a functional gauge during the setup for machining, followed by machining if the setup proves that the casting will assemble correctly with respect to its datums after it's machined. At the upper left is seen the go, no-go gauging of the 2 as-cast slotted holes, one in the horizontal dogleg feature and the other in the vertical feature formed as cast in the mold at 90 degrees to the dogleg feature. At the bottom right is the hydraulically actuated machining fixture designed to clamp the casting using its 2 slotted holes and the dogleg and vertical surfaces. The dotted lines on the top face of the fixture indicate the machining setup positions of both a left-hand and right-hand casting. Finally, at the upper left is a right-hand casting with yellow highlights showing how it fits into the machining fixture before the casting is hydraulically clamped. The functional gauging occurs when the casting is clamped. If it wiggles at all, then the slotted holes are not within position or size tolerance. The as-cast 90-degree angle is not in tolerance, or the casting is twisted or bent, or a combination of all 3. If it wiggles, the casting is removed from the fixture, not machined, and returned to the metal caster for evaluation, correction, or scrap. When the casting is clamped without a wiggle, a clearance hole for a shoulder bolt is drilled. Using these GD&T-based gauging procedures, 6,000 pairs of castings were machined and put into service in the hood mechanism of a Class 8 truck with never a rejection year after year.
Manufacturing engineering via 3 solid models, a summary. In both parts 1 and 2 of our first article inspection success webinar, the theme has been collaborative manufacturing engineering among separate manufacturing businesses when the casting design has been established and can't be changed, especially when the effort is a DLA legacy cold start and the awardee is a machine shop. In that DLA cold start context, notionally, 80% of the responsibility for first-time first article inspection success lies upon the contract awardee. We've learned that the pathway to success is collaborative manufacturing engineering, and the enabling tool along that pathway is the development of 3 successive solid models that are the platforms for success. Now, I will turn our discussion back over to Keith Sturgill, who will detail the roles of the first article test lab and engineering support activity at DoD sites responsible for legacy casting applications. He will also explain an important but less well-known role of the Defense Contract Management Agency in authorizing components for production.
Let's look at the logistics and procurement landscapes for a moment. Legacy parts are typically out of production, so the supply chain is broken. The original manufacturing engineering and tooling are lost, and many times contracts are awarded to a manufacturer who has never made the part before, thus the term cold start. The pertinent industrial base has shrunk by more than half since the weapons system was in production, and small demand quantities for maintenance and operational requirements dictate small buy quantities. Cold starts mean the manufacturing team must overcome, among other things, all of the causes of dimensional discrepancies that Mike has described, such as pattern maker shrink factor and widening of the tolerance band caused by degrees of freedom in the mold cavity, just to name a few. The difficulty of the manufacturing task, the high risk of failure, and the relatively low profit margin for the small orders combine to chase away many bidders. The September 2019 DLA Aviation Casting and Forging Summit documented that production lead time for cast legacy airframe parts is now at an average of 800 days. That lead time amplifies just how difficult it is to make these complex parts as a cold start. Awarding to the OEM isn't a magic bullet either, because their tooling and manufacturing engineering has also been lost, so their lead time isn't much better than the cold start first-time awardee, if at all. In our foregoing comments, we have completed our recommendations to the cold start new awardees, who bear that notional estimate of 80% of the responsibility for inspection success and 100% of the manufacturing engineering opportunity to get all facets of a legacy casting first article submission correct. Now let's turn our attention to the guesstimated remaining 20% of the first article responsibility for first article success and approval. To review, that notional 20% is spread among three functions on the receiving side of the casting first article submission. First, the first article inspection lab has about 10% of the responsibility. The engineering support activity that supports the weapon system involved has about 7%. And the Defense Contracts Management Agency that authorizes production has about 3%. You might logically be thinking, how can the DoD's inspection and engineering support entities have any responsibility for first article approval other than the straightforward evaluation? After all, it is what it is. Surprisingly, because it is less known than it should be, the FAR sections 502.209-3 and -4, which specify how first article contracts shall be evaluated, addresses this obligation. Quoting the key text, the contracting officer shall notify the contractor in writing of the conditional approval, or disapproval of the first article. The notice of conditional approval or approval shall not relieve the contractor from complying with all requirements of the specifications and all other terms and conditions of this contract. A notice of conditional approval shall state any further action required of the contractor. A notice of disapproval shall cite reasons for the disapproval. The basis of conditional approval is not specifically defined in the FAR. However, findings by the Armed Services Board of Contract Appeals, otherwise known as ASBCA, has provided clarification in rulings involving disapproved first article. Here's an example from an ASBCA ruling that defines conditional approval in terms of minor versus major defects in the context of manufacturing capability. Again, quoting the key text, the first article may not be disapproved or rejected because it was not in strict compliance with the specifications. It can only be disapproved if the defects are so serious as to demonstrate that the contractor cannot produce an item meeting the specifications. The phrase, the contractor cannot produce an item meeting the specifications, translates to manufacturing capability. So if an individual dimension or a subset of dimensions do not fall within their tolerance zone, but other similar dimensions do, then manufacturing capability is not the issue. As we have seen from our discussion of the complexity in accomplishing the manufacturing engineering of dimensions, A single or a few dimensions could reasonably be outside their tolerance zones and have no reflection on the cold start new awardee's ability to correct those dimensions with a tooling revision. Similarly, if the preponderance of the casting's surface finish meets requirements of the casting drawing notes, then a local area that does not meet those requirements should not be cause for rejection. A nonconformance can be noted to be corrected before production. So, and I want to emphasize this, how does the FAR provide for correction of nonconformances that are not caused by insufficient manufacturing capability? It expressly allows for conditional approval based in part on the Defense Contract Management Agency verification of correction of minor defects. That verification occurs during the government acceptance inspection at the manufacturer's plant. Such minor nonconformances are to be corrected by the contractor and verified as corrected by DCMA as its representatives inspect the castings at the contractor's site before signing the DD-250, acknowledging government acceptance and authorizing shipment of the contract quantity. We can now see how the first article, Inspection Lab's guesstimated 10% responsibility, and the estimate of Defense Contracts Management Agency's 3% responsibility for casting quality, can most definitely come to play in reducing the astounding 800-day average lead time for cold start new awardee legacy aircraft castings to be delivered. But what about the receiving DoD site? Their engineering support activities guesstimated remaining 7% responsibility for casting quality to contribute to the cold start new awardee legacy casting first article approvals. The issue here is outdated or incomplete technical data packages. Although DLA and the services concur that technical data packages are to be reviewed and updated every 60 months by the Cognizant Engineering Support Activity, unless that ESA were to have the metal casters or mold cavity tooling builders insight, it is difficult for the ESA to perceive what legitimately should be corrected in a TDP during the 60-month review. Since the bid window is typically only 8 to 10 days for a cold start procurement, and the procurement is often automated, a thorough analysis of the TDP by bidders is unlikely. If a bidder were to cite an exception to the TDP, the automated process sets a request for variance aside, and the bidder won't be successful, even though the bidder has been prudent. Further, 70% of the cold start legacy casting bidders are now machine shops, making it virtually impossible for casting manufacturing issues to be noticed during that 8 to 10 day bidding window. So, and again, I want to emphasize this, unjust or not, it is the cold start new awardee that vets the technical data package as the fresh manufacturing engineering effort begins. Without getting into the deep details of legacy casting TDP insufficiencies that have been discovered over the years of the CASTIT team's procurement support, here are a couple that would be unlikely to be discovered by the ESA's 60-month review. First, specification of A357 aluminum alloy with the T6 aged heat treatment. In this case, A357 is specifically identified by the AMS A21180 standard for 6 premium quality high-strength aluminum alloys. However, A357 contains a small amount of beryllium, as does its successor version E357. Beryllium is a known carcinogen and the fumes from melting and pouring alloys containing beryllium is a health hazard among aluminum metal casters. A new beryllium-free alloy, F357, has now been established with similar high-strength properties. A357T6 is unlikely to be available to a cold start new awardee because of the beryllium, and the ESA would have to modify the technical data package to allow substitution of F357T6. A second example, the drawing dimensions are insufficient to fully define the solid model that the mold cavity tooling builder always creates at the start of new tooling construction. Everything now starts with a solid model. Originally, when tooling was built by hand, the pattern maker, as they were known in those days, used latitude to blend together the features that were insufficiently defined dimensionally, resolving the issue with a blend. Now a drawing clarification is needed to properly build the solid model from which the mold cavity tooling will be created. So, it is very helpful if the ESA responsible for the legacy casting is responsive to TDP clarification requests. Even more helpful in minimizing cold start new awardee lead time, if this language were to be included by DLA in the procurement contract, as it has been included by DLA on aircraft egress and life support component procurements. DLA Aviation Contracting Officer grants permission for the engineering support activity to conduct clarifications directly with the suppliers. However, any clarifications that result in necessary changes to contract language, technical specifications, etc., shall be addressed with the post-award contracting officer. To conclude, we have seen that the DoD Testing and Engineering Support Site and the Defense Contract Management Agency can contribute legitimately according to the FAR and according to other types of DLA procurement contracts. Although the primary and vastly larger obligation is upon the cold start new awardee, we have seen that thoughtful, intentional partnering among the metal casting supplier team businesses can make first article nonconformances few. But the 74% of nonconformances that are dimensional or surface finish related may need assistance from the cognizant service or the DoD site. A combination of both would dramatically reduce the horrendous 800-day average delivery lead time statistic for cold start new awardee legacy castings. Julia will now rejoin us to lead comments from Castit in response to your questions and insights provided in the chat box. Here's Julia.
All right. Good morning, everyone. My name is Julia Speaker, and I am the Castit team lead. So while everyone is getting their webcams going, I'd just like to give you a little bit of info on Castit. So we're a team of application engineers, and we're working to solve some of the issues that come up regarding castings. So if you look in the handout section, there are two handouts. These just go over some resources as well as some projects we've worked on in the past. And other ways we may be able to help you out. If you're having trouble downloading it, no worries. When I send out the link to the recording of this webinar as well as the PDF for this webinar, I'll include this information. All right, so let me take a minute and introduce our panelists today. So we have Mike Gwynn. He is a casting design expert. Keith Sturgill, he is a metallurgical engineer who has copious amounts of experience with DLA and all of the government processes. Dick Tiano, who is a 3D data expert, and then Dave Powlite, who is the VP of Steel Founders. And there we go. I was going to say we should also have Gary Burrow, who is a 5th generation pattern maker and really all around casting guru. So I say let's go ahead and get started with some of the questions. So one question is, if it is a legacy part, is there really kind of this opportunity to do manufacturing collaborative engineering, or are we kind of just stuck with the TDP requirements? Keith, do you want to take a stab at answering that?
Yeah, I will, Julia. There is a chance for collaboration. Of course, as we've talked all the way through parts 1 and 2, the collaboration that's most important is with the supplier team, the mold cavity designer and builder, the machine shop, the foundry, all of those team members. That collaboration is the most important. Also, though, it is important to have a collaboration with the ESA. DLA does allow for a post-award pre-manufacturing or pre-production conference, although those are really rare. It's a possibility, but would have to be requested via the post-award contracting officer and also coordinated with the ESA site by the contracting officer. So it's possible, not really a likely thing that can be done, but probably the most likely collaboration would be done formally and on paper through the post-award referral request that the manufacturer awardee would submit to the post-award contracting officer, and what they call the PAR process or post-award referral process. And typically the question they might have would be submitted through the request for variance RFV process. So yeah, I would encourage any manufacturers that have questions early on when they're going through the TDP that they would engage one of these two methods, either the post-award conference or through the post-award referral process.
Good. It's good to know there's that opportunity. All right, so I'll direct this to Gary, and then maybe Keith, you want to chime in after. But do you have any suggestions for pitfalls, common pitfalls to look at or look for in either the contracts or TDPs when it comes to these first articles, as well as just castings in general? Gary, sounds like you're still muted.
Hear me now?
Yep, we can hear you.
Okay. So I think the things that we generally run across is usually somebody just hasn't reviewed the TDP properly up front, or they didn't really understand what they were looking at. If you're a machine shop, you're not going to understand a lot of the issues that may be covered on a casting. So if you've got your foundry chosen up front, which I presume you would if you quoted the job, you would think you have gotten a quote on the castings. But I have seen instances where a machine shop just says, oh, we ought to be able to buy that casting for $300 a piece, and puts that in their bid, and then they go out looking for a foundry after award, which can turn into a nightmare. So I think that having your foundry that you're going to use known up front, and then going to them at time of award, say, can you help us review the TDP from the casting side, could save you a lot of headaches. And then, as has been all through this, is the two of you do your manufacturing plan together, so everybody's on the same page. All tooling points are going to be worked from the same point, from the foundry level to the machining level, sometimes even on into assembly. But I think that would be the best path to follow to keep the least amount of headaches down and possible rejections.
Yeah, I'll jump in and add a little bit to what Gary said. There are a lot of pitfalls for someone who maybe is new to doing business with the government, or new to the first article process. And we actually tried to address this. We have what we call a first article punch list, which is on the AMC, or American Metal Casting Consortium's website. You can just type that in, Google that, and you'll see the resources there, which include the tips that we've prepared. One of them particularly is a first article punch list, and it details some of the pitfalls that we've run across over the past few years. One, for example, would be if the TDP has outdated paint specifications. Because of EPA requirements and OSHA requirements, most of the paint systems now are low VOC paint systems. So, and that's what all the painters use. For example, the aircraft paint systems are low VOC paint systems. Well, unfortunately, when they do the 60-month review, that might get overlooked as far as needing to update those paint specifications. So then the new awardee, when he gets his parts made and gets ready to get them painted, he finds out, oh, I've got a problem. My painter can't use this paint that's specified. So that's one. Surface finish, as we mentioned, I think Mike talked about in depth. Surface finish is another one because most foundries, they're measuring their surface finish with a visual comparator. Sometimes the TDPs specify a method known as a profilometer, a surface profilometer, which profilometer is not really ideal for measuring the casting surface finish. So you might want to get that issue resolved up front. And another one which we've run into, which used to cause a lot of problems, hasn't caused as many lately, is some labs tend to measure do their dimensional checks over top of paint and inorganic finishes like cadmium plating or something. Some labs don't strip those, and that can cause dimensional problems. Something that appears to be a discrepancy, it's really not, because if you look into the drawing, it says, measurements are on bare surfaces. So it would be wise to get how the lab measures. Is it going to be on bare surfaces or painted surfaces, plated surfaces, that sort of thing. And the last thing I'll mention is all of the first article documentation that accompanies the first article exhibit to the lab. That documentation needs to be very complete. All of the material certifications from the mill or whatever. If you're buying pig, you have to have all of those certifications. If you have special processes that you're using, make sure those certifications are included in the package. And we have an entire punch list that talks about all of those things that need to be in your documentation package, because quite a large number of first articles are failed because of insufficient documentation. So let me again encourage you to go to the AMC website, check out the CAST-IT resources there, the tips. I think it could be very helpful to you.
Yep, and I dropped that link to those resources in the chat, so you guys should be able to see it. I believe it's also in one of the one-pagers, but that punch list Keith is referring to is at the very bottom of that webpage. So I think we have time for a quick answer to one last audience question. So historically, COD start firms have had to pass first article processes and then wait for subsequent procurements to actually sell those products to DLA. Is this still a barrier to entry for new firms seeking to assist DLA? Keith, I'll direct it to you first, and then anyone else can pick up for a quick answer.
Yeah, this is a little bit of a difficult question. I think foundries, they're maybe bidding for the solicitation is a small quantity, so they're bidding for a small quantity. So for efficiency's sake, foundries like to cast all of the entire quantity and the first article at the same time. There's a risk in that, is if you fail the first article, you would have to scrap out those additional castings, the contract quantity castings. I think actually the DLA clauses at least imply that the production quantity shouldn't be made until after first article approval. So I think there's a certain amount of risk in a foundry making the entire quantity in the same pour before first article passes. But certainly I can understand why they would want to be able to make profit on the contract.
Julie, I might chime in on that too. This probably goes back more to part 1 of our webinar, but metal casters can make for themselves prototype castings that they don't finish. They just have the as cast surfaces. They may have fins from parting lines and core match lines still on them. But since this 83 or 84 or 89% of the non-conformances are dimensional or surface finish related, you can see as a metal caster from those quick prototypes the dimensional and surface finish difficulties that you may have. So while you're trying to make the engineering plan towards first article success, the ability to make prototypes for yourself and measure them without all the investment of finishing and heat treating and so on is a real opportunity to check to see where you really are, especially dimensionally, and the capability of the surface finishes without investing very much time or very much cost.
Good input, Mike. All right, so I think that is all we have time for. So I want to thank you guys for participating in today's first article success webinar. There will be a pop-up after you exit this call with a survey. We really do value your feedback. We try to incorporate it into our future webinars, so please fill that out. And then if you have any questions about anything we covered today, feel free to reach out to me. I'd be happy to discuss it with you. All right, have a great day, everyone.
Thank you.
Bye.
Thank you.